Well, welcome to our Maps 362 class, which is 3D modeling. I'm just checking to see if everything is recording properly here. So welcome to 3D modeling. This is where we get to really dive into laser scanning and LiDAR and talk about actual modeling and creating what does that look like. So what we're going to be doing for this course is starting out with the math behind modeling and talking about what does that really mean to develop a mathematical model. And then we're going to move into sampling, and we're going to talk about like how to calculate sampling rates. And then we'll talk about the actual models themselves and accuracies and everything that goes with that. So this module is a series of about 6 different PowerPoint slides. And then what I'm going to do is after I go through the PowerPoint slides, there's also going to be reference to other videos where I'm actually going to work through some examples with you guys separately from the PowerPoints, so make sure you keep an eye on that. So let's move into what is digital terrain modeling. So the first thing is we're going to get in Module 1, which is all the modeling components, and we'll be talking about what does it really mean to model a surface. So the first objective that we're going to come out of this is not all going to be following exactly word for word what's in the course outline. So we've been talking about that and how this course is a little bit different than my remote sensing. And just again, so if you're going to see objectives that don't exactly go word for word with the course outline, and it's just because I kind of have to mix and match throughout the semester and refer to those. So what you find in here is all going to cover everything that is in the course outline. It's just not going to be in order. So to start off, what is a digital terrain model? So digital representation of the terrain is really what a DTM is. And so that's what we're looking for, is just like how do we represent our terrain in a digital surface within the computer. So you're going to see a whole bunch of other terms that are out there. So there is a digital elevation model, which is that DEM that you often hear. So this is looking at an elevation above a datum, so anything like mean sea level and so forth. So DTM is actually like a bigger, broader version than that, because DEM really looks at the elevation. In Canada, though, there's a lot of confusion between what a DTM is versus a DEM. So the digital elevation model, we often say a digital elevation model is the data points. So if you go out and you collect data points with a GPS, or you go and collect data points with LiDAR, you've created a DEM with those points. Once you start connecting those points together, in Canada we refer to it as a DTM, so a digital terrain model. Now, if you were to go and talk to somebody from a different generation, or maybe somebody who's being taught differently from another part of Canada, they might interchange those again. So DEM and DTM are often interchangeable in Canada. Younger generations refer to the DTM as the actual model, DEM as the data points, and so you can you're going to hear both. So don't be like, hey, that's not what it's called, or Karina taught it wrong. It's just the way that in Canada it's just like, you measure your height in feet, and then you measure the length of your building in centimeters, right? So it's just like that weird confusion that we have here. And there's also a digital height model, which is found in Germany. Height just means distance from bottom to top. And then we got the digital ground model in the UK, just looking at relative height changes, because really the UK starts at the sea level, right? Because they are really close to that, and not a very big country, so or a series of countries, so they can use just like a ground model. And then the last is a surface model, which we refer to the fact that it's like bare earth, so we remove all the trees and the buildings and stuff. Or it can actually have those features. So we're like, we want to see exactly what is on that surface at that time. So we want to see the trees and the buildings and the bridges and all of that. So that is, those are some of the terms you might see throughout your career, and again, depends on what country you are coming from. So different methods used to represent the terrain. So paintings, right? So obviously we're not going to learn painting today, but that is one of them. Maps, we often see maps representing the terrain, so we can see everything from hill shading and coloring to where the water is and just locational information. We also have semi-symbolic or semi-pictorial, so here's an example of like semi-symbolic looking at cadastral maps, and just we can see lines mean certain things and polygons mean certain things, so that is that's another way to represent. Contour maps, specifically to that, we can see contours showing us that elevation. Shading, like I mentioned before. And then photogrammetry, just taking a photo of it. As soon as you go to put in put it in 3 dimensions and you take 2 images doing stereo imaging, then you are going to get that 3D view. We also have satellite images, so you can download satellite images and get different perspectives of the terrain that way. So if we can represent the terrain in so many different ways, why do we actually need to create a model? So a model is an object or concept which is used to represent something else. It is reality scaled down and converted to a form which we can comprehend. So putting something into 3 dimensions is great, but how do I determine a point in between points that I didn't actually collect? So there are many different ways to model. So a map is really just a model of what we are looking at. Like it can be a map of the ground, it can be a map of a building, it can be a map of all that. All of that is terrain models that we can work with. So, so with that, what are really the different types of models that we have? So generally speaking, there are 3 types of models. There's a conceptual model, which is really like what's in your head. So you visualize it in your head. It doesn't actually exist. You can base it on knowledge or experience usually, and it's usually the primary stage of it. So you're like, this is what I want it to look like at the end in your head. So what does that look like to come out? Now again, conceptual models, we have created those several times, right? So I get you to do workflows and algorithm design. Those are all conceptual models because they're not actually like the actual product at the end. It's just conceiving how do I create or move forward with this. Then we have the physical model, and so this is also an analog model. So sometimes you have them 3D printed, made of rubber, clay, plastic, etc. This can also be a map. Right? So it's actually the physical thing that's there. It can be digital as well. So we have analog there, but it can also be digital. So that's another major one. And the last one is what we're going to be focusing on, which is the mathematical model. So this represents a situation, object, or phenomenon in mathematical terms. It can be quantitative or qualitative, and it can be something called deterministic or probabilistic. So if it's deterministic or functional, it means that it only has one answer. If it's stochastic or probabilistic, then it means it can have more than one answer, so it's not a unique solution. And those stochastic models are really kind of a lot of fun, but we're not going to spend a lot of time working on those. We're going to really look more at the deterministic side of the mathematical modeling. So, so what we're going to do is create math models. And we're going to have some fun with that, right? So that's really important. But before we go too far, we have to look at what do we need to look at when we're going to choose the model. So things like accuracy, we understand that. Descriptive realism, so does it actually mathematically show what is there? Sometimes if you get into like higher order polynomials, like if you go to an order of 100, it's just like too crazy. Like it just doesn't look anything like what the real world actually looks like. So how much realism do we want it to look like? Precision, we understand that. Robustness, can I keep doing this over and over again and keep getting the same result? How much generalization do I need to do? And how informative is it going to be? That's what I mean by fruitfulness. So, we really need to follow that modeling, or follow these 6 different factors in order to choose our model. So then we can classify our models. So we can do mathematical or graphic. So graphic is that physical model that we were talking about. At the top, we have global and local. And so the mathematics of global, we have Fourier series, which I introduced Fourier series last semester. I'm not going to get you guys to do Fourier series mathematically in this class, so you can take a big sigh of relief. But then we have polynomials, and we are definitely going to be focusing a lot on polynomials. So bring out those like least squares adjustments, and we're going to be working with those. Other expansions we're not going to take a look at too much, but there are many other ways that we can do global modeling. And then local modeling, we're going to do both regular patchwise and irregular patchwise. So regular patchwise means that we're using like a normal radius. So we're going to say, okay, the radius of the area I'm looking at to create this model is going to be 150 meters. And then all the way through the entire ground area, then we are going to use 150 meters to determine our models within those areas. Irregular patchwise is usually based on number of points. So I can say, okay, I'm going to use 150 points to be able to calculate within that model. And then every 150 points as I move through the entire terrain in that area. So that's irregular. In graphic, we have point lines and areas. So you guys have worked with these before in drafting and even in remote sensing, GIS probably as well. So we're not going to spend a lot of time on creating the graphics of the models because a lot of software already does that, and we'll be using ArcGIS to do that. So we used to use something called Surfer, but Surfer's got to be really expensive software, so I had to say, okay, for my one activity, it's not worth the $20,000 that we were paying for it. So anyway, so that's why it is no longer with us. But we do have many ways of showing our point lines and areas as a digital terrain model. For the most part, in the end, with DTMs, we're usually looking at areas unless we're trying to create contours. So there's a process to all of this modeling. So first of all, we start with the bottom corner here with the DTM project. That's our planning stage. What are we going to be doing? Then we go into a design stage, and we try to figure out how are we going to collect our data. And then we figure out how are we going to classify that as well. So let's say we're using LiDAR, and we say, okay, we're going to get LiDAR. We're going to have, maybe even just as simple as off-ground and on-ground, or off-terrain and on-terrain. And that's what our classification is, and that's all we care about. So what information do I need from my LiDAR system in order to actually go out and collect the data? So at the sampling point, we have some calculations to do, and that's going to be included in like flight planning. You do that in photogrammetry, not in this class. So we're not going to do flight planning in this class, but we are going to talk about sampling for LiDAR and even just like GPS collection and all of that. So when you become a project manager, you'll be able to say, hey, I remember Karina teaching me this sampling rate, so now I can go back and do that. Then we go out and collect our raw data. We do some quality assurance with it, and then we reconstruct that raw data into a DTM surface. We need to validate that, make sure that it looks correct. Then we have put it into the application. So this is my presentation mode, and we create a product. Then we go back and we again check the quality of it because everything needs to have quality checked all the way through. Then you send it out to our user, and hopefully they say, hey, you know what, we want to use you again. So this is our next project. So that is kind of the cycle in digital terrain modeling. So how do we acquire this? So you guys should be very familiar with all of this because you have done stuff. So here is methods of data collection, total station, conventional leveling, GPS, that's all point-based. That's actually me years ago doing a highway survey. I guess I was out at Kananaskis doing that at the Kananaskis research station. So yeah. And then there's also area-based. So we have photogrammetry, SAR, LiDAR. You can consider LiDAR to be point-based as well, but it is, depending on what you're doing with it, there's two different ways of handling it. Because you guys do CAD-based stuff with LiDAR in our program, I am taking it into area-based, which is raster. So we're going to be looking at raster processing and analysis of LiDAR rather than looking at the point-based stuff. So you guys are familiar with total station information and leveling. You need a datum within a reasonable distance so that you can actually access it by foot. It's great for small areas. It's quite accurate. It has very simple post-processing. GPS is great as well because it's relatively faster. And it is also related to a height datum that is calculated through the satellites rather than and through the where your stations are set up, rather than having to post-process that later. And it is comparable to traditional survey methods for larger areas. It is sensitive to the environment though. So for example, high Arctic stuff, GPS is not necessarily the fastest or best way, especially RTK. It does require a lot more planning and quality control when you are using GPS. That float versus fixed situation, right? Making sure you have fixed. Then with area-based, 85% of topographic maps are produced using photogrammetry. So there you go. Even Google Earth goes from satellite to aerial imaging. And then it creates all its maps through the photogrammetry application of that. So this is great for larger areas. Photographs are taken using metric cameras. So back in 2004, we kind of talked a little bit about metric cameras. So just keep that in mind. And last is classification. So how do we classify our data? You know, what kind of film or spectral resolution do we want? What's the spatial resolution do we want? And what are we really trying to get out of that? So just an example there. So other types of area-based data collection is existing topographic maps. So if you already have an existing map, you can go out and access it and take a look at it. I mean, generally speaking, the ground doesn't change that much over like a few years, but over decades or centuries, then yes, it definitely does have a little bit more of a change. It's more the human-based stuff that changes faster than the natural. So, but we have to be careful about generalities. So if they've generalized something, what are we really looking at? And what is the scale? Because again, you only get such a certain accuracy when you scale something down. Then also just looking through vertical contour intervals, right? Like a contour interval is about accuracy is about a third of the contour interval. So you're not going to get super high accuracy unless you're like, you got contours every like centimeter, right? So just to, again, really watch this height accuracy. And again, you don't want it to be overloaded with contours, and depends on what you're looking for. So existing maps is a way to go, but they're not necessarily the best. So for example, this one, we really don't have a lot of information on height, right? So what do you do with that? So it's not, obviously this is not a great application unless you were just trying to find the edge of like the Hudson's Bay here. So here's another couple examples. Now we've got some contours in this case, so these are a little bit better. We've got our 1 to 50,000 NTS sheet, and this would be even closer in. That one is 1 to 17,600. So again, you're getting a little bit better accuracy as we move in, but which one would you need? Which one would you use? That would be up to you. It depends on the application. So next one is INSAR, right? So I could go on and on again about microwaves. I think that they're like the best thing ever. So they are very sensitive to variations of the terrain, and they have a similar concept to photogrammetry. They just use wavelengths rather than using the actual visual of it. So we can create 3D images with no problem with 2 SAR images. And it's just a lot more complicated, right? So remember that. So, and it is also, it has to have like the transmitter and receiver, and those are generally kind of in the, like they're from the same sensor, but they're in 2 different spots. And it gets more and more complicated as we go. You guys have seen this one before. And just trying to figure out, how do I determine my image? I'm looking at the near range and far range and swath width and 2 different data points that we actually collect the data, et cetera, et cetera. Here's my master's work that we did up in Reindeer Station. So how do I georeference all of that? What's the area? This is the area that I was looking at right here, which is Reindeer Station. So it's a little bit of a different type of map, right? So but again, that's a whole other course in itself. So we talked a little bit about microwaves. We talked about the complexities of it. We talked about how to produce those, but to actually get there and like to fully create that. Some of you guys did a really good example with that. You actually worked through the Sentinel toolbox, which is great. But again, really to understand all those different processes, that's a whole other course itself. So we're not even going to get there. But what is really exciting is the LiDAR. For this course. I will sadly say that I will not like refer to microwaves throughout this course. I'm going to talk about lasers. So LiDAR is an active remote sensing system. So it sends and records its own data. It is great for high vegetation areas. So, because it can actually see through like a canopy, which is great. It's great for 3D city mapping, and it's good for surveying power lines because it has that. It's not restricted to a pixel. It's restricted to just the actual data point itself. It is very complex though, so there's a lot of different parts to it because we have a lot of different sensors, and we'll be getting into that when we get to LiDAR. It also depends on the material it hits, the angle that it hits. There's so much that goes into LiDAR. That's why we have most of a course that focuses on it. Now here's a couple examples of what LiDAR can look like, and the fact that it can see through those trees. Trying to model those trees. We can also see these towers, and we can see the different parts of the towers, which is really effective compared to like a photogrammetry application, because again, we don't have that three-dimensional data right off the bat. We need a lot more images to be able to get all these different parts of this tower. And plus the trees around it, right? Like how close are those trees? How tall are they compared to the tower? So again, photogrammetry can only help so much in these kinds of situations. So just as a really quick summary, let's go back to this. So there's a lot that's involved. There's a lot of different parts that are involved. We have to go through this whole process to be able to get to a final product. But the data collection itself comes from many different methods. And as we try to improve our accuracy, we end up having to go a little bit further with complexities, right? So there needs to be more included, especially if you're covering large areas, because you need to do it quickly and effectively, efficiently, and with a high accuracy. So, so that's DTM. You guys have seen that there's a lot to it, whether it be creating a map to modeling a tower, right? So, and looking at tree heights, looking at tree types, looking at what's on the train, what's off the train. So there's so much that goes into this. So in the next video, we will continue on with talking about the modeling, and I think I get into sampling at that one.